Recording in progress.
All right, so where's the, yeah, so the microphone seems to be moving there. So let me share the screen. Yes. The what? That's, no, that's not, I think that's just, you saw it really fast. Did you see it like right away? Because sometimes it takes a couple of hours for it to go to what is called like high definition. Are you sure? Did everyone else have that problem? I've never had that problem, but what I can tell you is, because I use the same methodology, right? What I can tell you is if you see it right away, what is it? YouTube hasn't had time to move it to high definition. So they do like processing in the background. Double check again. And if you do find specifically, hey, this is the one, and that your internet connection is not the issue and all that, send it back, send me the, and I'll take a look. You know, just say like at 3:35 in this video, there's a problem. Huh? Is bad? 4K, right? That's good, right? Yeah, yeah. So I think that probably I know that happens like when I was learning about it's just right away it looks bad because YouTube takes a while to do the high definition thing. All right. So anyway, we are recording. We recorded all that. All right. So as I was saying, today is a very important lecture. We're basically just going to start with, hopefully you had a week now to work on the linear regression code. You had a homework assignment that was pretty easy, that's due tonight, correct? And so today we're going to just take that initial code of linear regression. I'm going to copy it literally, right, to a new file, and then we're just going to modify it and start looking at neural networks. Okay, guys? That's it. And you'll see that it's very simple. And so at this point, you will start to look at, you know, this is a very simple thing. And then we'll have another, the second example that we will do at some point will be with CIFAR 10, which is images that are 32 by 32 of different things in color. So that's literally like, you know, a 70,000 data set. You know, at that point, you really can do a lot, you know, that's what I want you to understand, that once you've done CIFAR 10, you can tackle many problems going forward on your own, okay? Because really, you know, as long as you can always take your data and your problem and convert it into the same format that we're going to use in this example, you can do machine learning. All right. So and then so this today I'll just do this probably, and then we'll do like some slides just to kind of some of the terminology, better define it, etc. All right, so it shouldn't be that much coding today because we are at a really good point where I'm introducing, as I said, CIFAR 10. And if you have any questions, just let me know. Okay, so. All right, so let's start, open up a terminal here. Okay. And we're just going to navigate to okay, so we're going to do this problem. So first thing, let's find the file. Okay, so we're going to go to ITS 520 fall 2021. So so I think SGD, right? This one, stochastic gradient descent, scratch learning. This was the last file that we looked at last week. So what's so great about this, what I was saying is that I'm trying to create this template, right? And the idea with this template is that you always have a way to start. You don't have to like, you know, have all this crazy code and you never know even where to start, right? That's usually, I would say, the problem with you know, machine learning, deep learning. You just don't know where to start with the code, and you get maybe stressed out about it. And that's why it's good to have this idea of a template. You know where these things are always there, and it's just about the data, it's just about modifying this and that, okay? So we're gonna follow that same idea with the template. So all I'm gonna do here, I'm gonna check the permissions of these files. Okay, so you can see here, pretty straightforward. So I'm gonna copy stochastic gradient descent, okay? And I'm gonna create a new file. And let's just call it, this is going to be, let's just call it simple neural net. Okay, so simple neural net. So I'm going to say simple neural net.py. Okay, so basically I'm not going to have to explain everything that we've done because a lot of this we're just reusing, right? We're just reusing a lot of the code, and so we're really just going to focus on modifying certain parts of the code itself. So I will do a bit of a review of what we did the last time around. So if I go over here, we can now open simple neural net. So I'm going to open the file. All right, and you can see it's the same file as before, but now we're just going to add a few more components to it. All right, so this is no longer basic learning with linear function. That's what we did before. And we're going to continue with the same data, but we're going to modify it a little bit. So in this case, now this is going to be a simple neural net. A simple neural network. And believe it or not, it builds on top of that idea of y equal mx plus b. We're still looking at that function, and we're just going to start to build on top of it. So the libraries here are going to be Torch, NumPy, ImageIO, OS, Matplotlib. We have the torch.optim as optim, right? You guys remember this is where we got the optimization algorithm that does the derivatives. We talked about all of that, right? How to calculate the weights. So hopefully you remember all that. Now we're going to add a new library, right? So we're going to add a new library, and as you might imagine, we're dealing with neural nets. So guess what? We have a neural net library. So we're going to do import torch dot nn as nn. Okay, so we add this library here. And now that's basically the library that's going to help us to build our neural networks, okay? The data is actually, just to keep it simple, it's going to be the same data as before. So I'm not actually going to change the data, and that way you can see the contrast between what we did with the simple linear regression and now how we're just adding the neural network. So I strongly recommend that, if you can print out this code, the original one from last week, this one, kind of look at the difference. But that's why I'm doing it this way. So you can see how we're building on top of that idea. So I have, the TC and TU, we already know this, right? These are the temperatures, same data, same values, nothing has changed there, right? Then we have our samples here. Now we might need to do some additional tricks to this data. So for instance, here we converted the data TC-TU into tensors originally, right? And we had the TCU and TU. Now we're going to make this, if we want, we can make it into a column vector. All right, so let's take a look. If I print TC dot shape, right? So I want to print that out. All right, so we're going to do print. And then I'm going to do an input here just to halt the program. All right, so we can Control X, Y. And of course, I always forget to bash. And then we're going to do conda activate PyTorch I36. Okay. All right, so we're in the environment, so now I'm going to run it. Simple net. All right, and you can see there size 11, that's the size of the data right there, right? Now, as one thing the one thing that's always tricky with these problems, which is why we spend so much time at the beginning looking at NumPy and tensors and tensor operations, is because the dimensions of the shapes of matrices and vectors, right? That's the hard part of this that we have to kind of play with. So right now, what we're going to do is we're going to actually play around with the dimensions a little bit, so, or the shapes really of the vectors. So let me get back to the file first, and that was simple. So now we learned about unsqueeze, right? We learned about unsqueeze and how unsqueeze can add, you know, dimensions, if you will. So let's add here for torch tensor TC and torch tensor TU. Let's just do unsqueeze. Unsqueeze. One. Okay, so notice, you know, I'm doing just that. And now let's see what it does to the shape of TC. And actually, let's print it out. And these are the things that when you're doing your own machine learning, it will always be kind of an issue to look at the shapes, always to kind of imagine the shapes of the vectors and the matrices, and to make sure that they align correctly. So let's go ahead and run it now. And you can see what happened there a little bit. We added a dimension, right? We added a dimension to it, which basically made this into what is called a column vector, right? So we've made the data now into a column vector, okay? And so just so that we can process things a little bit better. Now that we have this, so notice basically, you know, I've done that step. So now, and this is just going to help us later on. So now that we have this, let me remove this input from here. And the next step that we would do is basically splitting the data, right? Just like we did before. So this, we can just reuse the code as we have it, most likely. So let me just confirm we have the number of samples, TU shape, right? Then if we want to get the number of validation samples, we're just going to take 20% of the number of samples and the integer. So that's pretty much the same. Then I already explained in the last video about shuffled indices, right? We spent some time on this, so we don't have to do it again. So just look at that video if you'd like. But here we have, we do that. We have the shuffled indices. Then we extract for train and for validation, right? And we also talked about this last week with the slicing, so nothing has changed there. There are many other ways of doing this, by the way. So you'll see a lot of this online, etc., of many tricks. All right, then we printed the indices, and then we sliced them out from TU and TC. Right, we have our tensors, our indices now separated out. Okay, and so this is for train, and this is for validation. So we have, these are the train TU, TC. These are the validation TU and TC. Okay. Now the next step is, as I said, you should always have a section in your template called normalize. Normalize the data. Okay. And that is almost always, if your data, especially if your data is not very similar, it will improve your results considerably. So you should always have it. In our case, our data is kind of very fictitious, right? And so it really doesn't matter that much right now. So all we're doing here, honestly, is making it a little bit smaller. But later on, we will look at slightly more complex methods of doing this. But the idea is basically you take all your data and you kind of make its mean, you know, the mean of it, you want it to be 0. So you, through an equation, you adjust it to that, right? Have a certain mean and a standard deviation, and hopefully all of it being within like -1 and +1. But anyway, this is all that we had done before. All right, then we visualized the data in the previous example. So that's also already reflected there. Oops. Sorry. All right, so we've looked at the data and we visualized it. That would be pretty much the same. And then after that, we had the model here. Remember, this was just a linear equation. However, now we're going to start playing with this, okay? But what's great about this is these two functions that I created, model and loss function, they will always be there. The functions are there. What's going to change is what goes inside. But that's a really nice system for a template because you always know, okay, I definitely need a model. I definitely need a loss function. But what does it look like for this particular problem? All right, and in your arsenal, if you will have all these variations of how to approach it. Okay, so we're going to have then the model, the loss FN. Oops, I keep doing that. I'm sorry. Keep forgetting all this. All right, so we have the model, we have the loss function, and then we have the function train loop, which is this one. So these are pretty much the same functions. We're just going to tweak them a little bit. Now, in particular, what I like to do is I like to usually refer to this as architecture. Or, you know, most people will do that. They refer to this as architecture. The architecture just means what does the neural network actually look like? Okay, what does the neural network actually look like? And then remember down here, we have this section where we basically say call everything, right? So this is where we call all the functions. We're going to call the architecture, etc. Okay, you can see that in the loop. And then finally the results. So we have you know, where we call train loop, etc. And then we just print out the results. So in this case, let's start, I guess, with train loop. All right, it's usually sort of the beginning. So let's start there with train loop over here. So in this case, we can do so our train loop. Gonna make it so it doesn't return a result. So as you can see in a previous example, we returned a result. In this one, we won't. Okay, so just a regular train loop like this, but we're gonna add a few other things to the train loop. So we have the number of epochs, which we have discussed, which is 3,000. We have the optimizer. Now it's a good idea to also pass the model into here. Okay, so we're going to pass the model into here. So we're going to need to modify our code accordingly. Model. Right? And then after that, we're going to remove the parameters from here. Okay. And instead, we're going to pass on the loss function. So we can say loss FN. Now, eventually, I'm not saying that this has to be done exactly like this. Eventually, you guys will find the thing that you want. But I do strongly believe that you should have a template that's the one that's the most comfortable to you. Okay, and it's your go-to. You know, you always start with that and then modify. You should, in fact, whenever you run this, you should, in fact, always start with one code that you know works. Run it on a set of data that you know works, right? Just to make sure. So, for instance, Cypher 10 is a good one, right? Always run it. You start with that baseline. You know the code works. It does the thing that you want it to do. And then you start modifying, all right? It's kind of the best approach. So loss FN, oops, loss fn in this case, we're going to assign to it some loss function. All right, so in this case, you know, we can say, for instance, just leave it as question marks actually, and we'll come back to it. And then we have our data train TU, that's just train TU norm, val TU, that's val TU norm, train TC, that's train TC, and val TC, that's val TC. So we have the loop here, or the train loop basically defined. I'm going to take out this result given that we don't have, and we might just explore other ways of printing out results. Okay, printing out results. But as you can see, we're still working with that temperature data. All right, now that we have this, we can specify over here. We're going to need a function, right? So we're going to need a function model because that's what we said we wanted. So model, and what's model going to be? So we need to figure that out. But the great thing about this is, this approach that I'm taking is that it's going to make it very easy to change architecture. All right, it's going to make it very easy to just change one line of code and you flip back and forth between however many different architectures that you want. So for instance, the next homework assignment I give you could be something like, all right, try 10 different neural networks of these many hidden layers. Try this, 2 hidden layers, 3 hidden layers, 4 hidden layers, 5 hidden layers, So basically you'll be easily able to change that, okay? And that's really the idea. So we have the model here, and we're going to define that in a second. Let's take out this variable. Now in the previous example, we did, we passed the parameters like this, and that's a way that you can do it. This is just another way. So we're going to take that out. We're going to take this sort of out of the, just try to make it a little bit more concise. So we have the model, then we have basically the optimizer. I usually only like to call, the model first, the optimizer second, and then some kind of a prediction, right? So that or evaluation. So usually kind of limit the template as much as possible. So the optimizer in this case is still going to be stochastic gradient descent. Remember we said last Monday that this could be the atom optimizer as well, if you've heard of that. Over here, we're going to move this a little bit, just rearrange the way it looks. Okay. And so basically the learning rate, we're just going to, code it in here, directly, make it a little bit cleaner. So I'm going to do 1e minus 3. Remember, something like 0.001. All right, that's always a good number to start with. You can play with that as much as you want. And then later on, as I said, when we go over the slides, a lot of these concepts will make a little bit more sense. Now here in the params, this time around, we might just keep the parameters in the model itself. So I'm just going to say model dot parameters. Okay. Obviously, we need to define model, right? So that will be the next step where we need to go to kind of provide more information. So now that we have this, right, we've defined the optimizer, we've defined we need to define the model, but at least we have a variable now that can be passed into the main loop, right? We also need to define what loss function we want to use, okay? And that there's many loss functions out there. Usually it's going to be something called cross entropy in general for classification that we're going to be using, but we're just going to play with a few, okay? Especially right now, we can just introduce a few, just see how it works. And then on your own, you'll have by now, you'll have many loss functions that you've seen. Play with them, try them out, right? Now, some are for regression, some are for classification, but in general, you can play with them as much as you can. All right, so now that we have, if you notice, we have the train loop defined, we have the optimizer, and you can almost see that I'm working my way back, right? It's like I'm starting at the end, and then I'm trying to work my way back. So the next thing we probably want to define before we tackle the training loop, which is usually the big one, is what are these models? All right, what are these models? So let's go over here. So I have model. Obviously, I need to provide the architecture here. What is the architecture? You say, or I said, this is a neural network, right? So what do I mean by that? So let's go here to where I have architecture, and you can see now I want to specify some function. So I'm not going to be using this one anymore. So I'm just going to get rid of it because I made model into a variable, right? So instead, I'm going to define different architectures here. So the first one that kind of makes sense is the same linear regression, right? We're just going to do it in another way. All right, it's the same linear regression that we had before. So I'm just going to say model FN linear. Right, you can see that there. And this just returns. Now, what I'm going to do is instead of using the equation that I had coded before, I'm going to use the built-in NN modules functions. All right, the NN module is basically designed to have all these functions built in. So here I'm going to do NN dot linear. Right, so NN dot linear. And you can think of this as the same thing as what we had before, the linear equation. Okay, and so here we just specify the parameters that it takes. So 1 and 1. All right, and so we build the we build the network as we want to do it. So 1 and 1, basically, because we were just predicting from one variable, one input to one output. All right, this is one model that we can define. But we can define other architectures. So in this case, we have in this case, we're going to build. So this is, let me write it on the board. So this is just basically like that, right? We have one input and one output. Celsius, right? Fahrenheit. Make sense? And then there's just one connection. That's the linear model. That's what we had before, correct? That's exactly what we had before with our linear function. However, now we're going to basically throw a lot of firepower into this, more so than we need to. You see that? What do I mean by that? I mean, I'm going to try to build this same thing, but with a hidden layer in between. You guys see the difference? Still the same input, still the same output as before. Here there was nothing. Now I'm adding an extra step. Why am I doing that? That's a neural network. A neural network is giving more capacity for the computer to solve the problem. Does that make sense, guys? All right, and that's what we're going to do right now. So in this case now, I'm going to create a new function. Notice that both of these functions are going to be interchangeable. All right, and that's the beauty of it. So for instance, I'm going to create a new function called model FN NN 1 hidden. I'm being very explicit there, right? So I'm just saying this is a neural net with one hidden layer, okay? And so it's basically the same idea, but more connections, The idea is like, think of the brain, right? You have a brain and sometimes you want to solve a problem. Wouldn't that be great to have another brain and throw some of the work to that other brain and have that brain maybe figure things out better? That's kind of what we do with neural nets, right? We're just throwing in these hidden layers, giving it what is called more capacity to solve the problem. All right, so in this case then, I'm going to go ahead. So 1, 2, 3, 4. And I'm going to now this is for those of you that have ever used Keras, this looks a little bit like that. And I think both of these, it must be the best way of doing it. So we're going to create some variable sequence model. sequence model. Okay, and now this is where it gets, this is where now you start to write neural networks. Okay, this is where, as you start to build neural nets, notice this is not a deep neural network. Why is this not a deep neural network? Quite simply, because there's only one hidden layer. So this is actually multi-layer perceptron. This was just a linear regression. This is a neural net, but not a deep neural net. For it to become a deep neural net, all I have to do is add one more or many, right? But that's the definition. So this is what I said. So last week, when we now introduced the linear regression, I said to you guys, well, you already know how to do 60% of deep neural networks, right? Because it all builds on the next level. So now here we're going to do the magic. Basically, it's NN dot sequential. Okay, and this module then, this is when you start to look at deep learning and everything. This is what starts to introduce something called convolutional neural networks, recurrent neural networks, transformers. All of these things, are architectures that you can build with this. And then we're just now building the very simplest of them all, which is the multi-layer perceptron. So here then, kind of the way that you can write this is you do sequential. And then here I'm going to do sequential. Okay. And now we're going to build this architecture. Okay, we're going to build this architecture. So there's a specific way that you go about it. Okay. First, so it's a little bit interesting how it can be done. But basically, we're going to start with this one, right? What is this one? Linear. Linear is, just one, right? Just one connection. So we build kind of these linear ones, but we're going to specify that we want multiple connections. If you think here, just if you take a snapshot of this one, there's basically 13 of these. You see that? There's that one, that. They're all independent in a way, right? So you will eventually in here need a way to kind of combine them, and you combine them through a function, but they're basically transformations or mapping functions of inputs to outputs, and then these outputs are going to get mapped to this other one. So this outer circle, you can think of it as whatever the result of this operation of these 13 goes to a function, any function. So right now I'm just going to use a function called a tangent, and that's just a function is just my result was 3. Now I plug it into function whatever, and the function will do its thing to give me another value. Does that make sense? All right, and we'll look a little bit at what the definition of a function is, but keep in mind, linear means literally linear, right? So it's a linear behavior of just adding things together, whereas when you have a function is the thing that creates these nonlinear options, right? So for instance, if we separate data, right? When we separate data like this, a linear separation is that, right? A nonlinear separation of that same data would be something like a curve, right? It's no longer a line. That's what we mean by linear and nonlinear, right? And when we're using linear functions, like I'm about to do, I'm basically implying in an intuitive sense, I'm only using instruments like this to separate the data. Some people might argue that this is a better fit of the data, right? A curve, right? And this has problems in itself as well, but intuitively you should think, oh, that function or some other functions allow me to curve the line, modify. You see that? That's the intuition. So that's why I want to do that. So how do I do it? So obviously that idea, think about this. There's an idea in math and everything of how you do things. You have to write it in code some way. All right. So there's basically a standard convention that works that allows us to write these things. It's kind of strange because you would expect it to be a little bit different, but you expect with functions a thing that's within another thing, that's within another thing, that's within another thing. That's kind of how you would expect functions to work. This is a little bit different, and that's why it's called sequential. But it kind of implies this idea that the results of these now go to a function. You guys see that? All right, so let's take a look at how that works. Keep in mind, all we're doing is that simple architecture. So we're going to do nn.linear like that, right? That's the kind of like we had it before. But instead of 1 to 1, like we did here, right, where we only created this architecture like this, now we need to create an architecture with 13 of these. You see that? So intuitively, if for the top one we did 1 and 1, intuitively we would do here what? 1 and 13. You guys see that? And that just means this first part from here to the 13 over here. Okay? Yeah, go ahead. There are 13 nodes in the hidden layer. Yeah, so I kind of. Good question. Why 13? Is it a magic number? And no, I just make it whatever you want. 26, Usually, though, you actually want neural nets to follow a funnel shape. So it starts at inputs that are really large, and then you funnel it. And that's the idea of forcing people or forcing things to work with fewer resources every iteration. It forces efficiency, right? If you have a lot of capacity, you're gonna, the neural net is gonna start to philosophize about things, right? You don't want that. You want them to go to the point. So the funnel shape is actually the kind of what you want, but obviously here, it doesn't have to be like that. It has been proven experimentally that it works better. Does that make sense, guys? Is everything making sense so far? All right, so again, you're creating your first multi-layer perceptron here just for linear regression for the problem of temperature, right, that we were exploring before. So I've done the 1 and 13, right? So then add a comma, I can add a comment here. These are very important. So say 13 neurons in the hidden layer. Okay, I recommend that you write that in there so it reminds you of that. So it's like explore this in 13 different ways. And then after that initial exploration, get the result, which is just one output, remember. Now we're going to go, but we want to run these results through some function. What function? There's a set of functions. And again, these functions are necessary, as I said, if you want to, in a sense, give more power to your neural nets by taking them from this to that. It's just an intuition that you should have in your mind that neural networks allow you. This is great. Linear functions are great. They're great in the sense that they generalize really well. They're very good, generally speaking. But it has been proven that what you want is functions that can approximate any problem. And you could argue, for instance, intuitively, that not all problems are linear. You see that? But this one, by having this structure, we can approximate anything. If it's a linear one, great. But if not, it'll try to approximate something a little bit different. All right. And so the intuition is, for instance, for that problem, it would try to build a more curvy or line, either fitting through the data or separating the data. So then let's proceed. So given that I'm at this stage now, basically the inner square, right? What I need to do now is run it through the function. So this is where I would say it's not putting the result of this inside a function, but instead we just, say NN, oops. And this is, as I said, TensorFlow, Keras, PyTorch, they basically all do it this way, okay? This is kind of the approach. So if you ever come across Keras, you will already understand in TensorFlow because it's very similar. So now you do 10, 8. And as I said, there are several of these functions. They're very well explained in the book. I recommend you take a look at that. Usually we're going to use like sigmoid, tangent, and one called ReLU. Okay. Right now, we're kind of just trying different things. Eventually, as we start focusing on problems, you'll see that you have a tendency to start using specific ones, specific loss functions, specifics, activate. These are called activation functions. Maybe I'll write that in. ReLU, sigmoid. So what's important here for you to take away is that this is your first attempt at creating a nonlinear function. Okay. Now, neural networks have a definition. They're called universal function approximators. And what that means is that in theory, they can approximate any function in the world, any function in theory, given enough data. Remember, we started with Kepler, right? And thinking about Kepler and how it works. So solving Kepler, solving black holes, obviously they're trying to solve intelligence, right? With this, I don't, our brains may be more advanced than that, who knows? But they're called universal function approximators. And this little part here is what adds these nonlinearity attributes. So at this point, just by doing this, we are basically at this stage, right? This is done. Now we need to do the second part, right? So we need to do the second part. And that one needs to be a linear prediction, right? That needs to be a linear prediction because we're still predicting numbers. Remember, we're still predicting some kind of a temperature or Celsius. So we're going to do nn dot linear. In the future, when we do classification, we are going to add something like nn dot softmax, or in some other cases, nn sigmoid. We're going to start adding that. But here for this problem, we want this to be any value. If we put in, for instance, if I put in here sigmoid, for instance, what would happen to all the results is that now all of my temperatures would not be 72 degrees or 80 degrees, right? Or whatever it is today. It would be what? Something between like -1 and 1, or something between 0 and 1. You guys see that? That would be the outcome of it, which it's not necessarily wrong. If we, let's say it's sigmoid, we want to treat it as a probability, right? We're almost going to be, we could treat the temperature today as a probability of being really hot versus probability of not being very hot by putting it in a range between 0 and 1. Does that make sense? But we're not going to do that. We want literally temperatures, like what is it, Fahrenheit, So we're not constraining then that value. And so we just don't add anything, right? And so we just go back to the linear part. And the linear part, this is called architecture, because one thing that is critical is we have to tie the dimensions, right? Remember, we always, in the previous one, it's very obvious, 1 to 13. You guys see that? So now in this step, what is it? 13 to 1, right? 13 to 1, exactly. So that means there are 13 neurons in the hidden layer, and there's only 1 in the output. Do you guys see that? Does this make sense? All right, good. That's it. I mean, hopefully, if you understand this, you've got a really good, because that's the beauty of PyTorch. It's meant to be easy, right? It's meant to be as easy as possible to be able to create these architectures, right? And so that's what I want you to take away from this. And then usually, as it's really what's hard is getting the data in the right format, randomizing it, normalizing it, all that stuff. That's hard. But this, it's pretty, it's meant at least to be pretty simple. Are there any questions, guys? All right, good. So it looks like you're getting it. All right, so we've done here, if you notice, we've got 2 models, model FN linear, right? That's defined 1 to 1. And then we've got model FN NN, one hidden, which is a shape of one neuron input, one hidden layer of 13 neurons just by choice, and then one output of one neuron. Okay, there's 3 layers there: the input, the hidden one, and the output. Okay. All right, that's great. So now that I have this, let me get rid of this space. All right, so 13 and 1. Let me add a comment here just so that you don't forget. So this will be one output neuron, and it's only a linear. All right, then if you want, you can do, remember we're in a function, so 1, 2, 3, 4. So you can do print sequence model. So certainly PyTorch this is something that it's a lot easier to visualize things in PyTorch by far than say TensorFlow 1, where it was really difficult. All right, and then of course it's a function, so we return sequence model. Okay, so we've got our architecture. So now that we have this, we can go back, loss FN. We don't really need this one, although we could in the previous example, we were doing this linear regression like this. Remember what I said, that you certainly can write out the equation. You can totally do that. And that's very helpful when you guys are, working for Facebook and, you're building some kind of a research project and you're going to, get in there, right? But otherwise, you're just going to use the built-in functions that are there. So I just did this to kind of show you that you can, but instead I'm going to use the built-in functions. So as you can see now, we're going kind of from like more academic way of looking at the algorithms to the more like practical way of looking at the algorithms. All right, so I have here then my architectures, linear, and I have my train loop. We still need to, it's probably the same one. We just kind of have to look at it a little bit more. Now here in model, where we call everything, we are ready now to, and this, I have a typo here. Yeah, this should say parameters. Sorry about that. Make that correction, parameters. All right, so we can define the parameters kind of outside, look at them, or we can just call them from within the model itself. As you can see, PyTorch is very flexible. You should try all these things, find your own style. That's ultimately what it is. But I firmly believe that having a template is a good way of going about it. And certainly even I like to start with some code that I know runs, make sure it gives me the results that I expect before I start tweaking it little by little, because it can get pretty complex. So now we're ready to decide which function we want. So let's go with, let's actually write both of them. So notice how this is nice because, you just have to make slight changes here. So I'm going to comment out the bottom one. So we're just going to use the simple net. Now the difference in the results will be very negligible. Obviously, with other data sets, it would make a big difference between linear and nonlinear. So let's let the bottom one we'll call later, but let's let that one be model underscore FN underscore NN one hidden. This is just kind of how I do it. I like to say like one hidden, two hidden, three hidden, that kind of thing, or CNN, or just to know which one I am invoking. And then this is going to be model FN linear. Like that. All right, so we're going to call. So we're going to start with the linear function, obviously, this top one, which is pretty much what we did on Monday, right? Exactly what we did on Monday, last Monday. But now we're using the NN built-in function and just to see our results. All right, so I removed the loss function that I had created from last week, right? And so therefore I need to replace it with something. So in this case, let's see, I am just going to, where did I have that? It's in training loop, right? Yeah. So in training loop, I need to specify a function. So as you can see, it can be a little bit complex by defining a separate function, equation, everything. That what was the name of that? Least squared errors, right? Right. That's also sometimes called the MSE loss function. It's the same function, right? So maximize squared errors. I think it's MSE, something like that. So, but they're basically the same idea. So then, instead of writing it out, just use the built-in, PyTorch version. The advantage of that, I can definitely say that sometimes when you write out the equations, you end up with errors, like little numerical methods types of errors, just like, there's an underflow of dividing by a number that's so tiny that it's almost zero, little things like that, right? That can happen, and so you get errors. The beauty of using the NN models built-in functions is that they always check for this. They're highly optimized, so you're very unlikely to get that type of an error. Do you see that? So in this case, we're just going to call that same function MSE loss. You guys see that? That's it. So we just add this in here instead of defining the whole thing. There are many functions of this type in PyTorch and in all deep learning algorithms, right? So, but usually we're going to end up just using a couple, MSE and something called cross entropy. However, as you get more advanced in what you're doing, you'll probably start exploring other things as well. All right, so then the train loop should be ready now. It's got the epochs, optimizer model, MSE loss, the data. Okay. So now, what do we have left? Oops, sorry. Let me actually save because I've added a lot here. All right, so then the last or the next step that we want to look at is we want to check the loop, right? So let's go to the training loop. And we're just going to make the modifications that we need to. Obviously, we've added a few variables, so we need to make sure that checks out. So we've got n epochs. We've got optimizer. Here we added, instead of params, we just added model, right? So we can take this one out. So now we have our model in there. We're going to use the built-in feature of its parameters in there. Usually you don't have to look at the weights. I mean, I showed you in previous examples that you can, and if that may be a tool for you to get further insight into what's going on, but in general you don't, right? You don't look at that. And instead, what you start to look at is the metrics that we need to cover. That we definitely need to cover soon. So far, some kind of a metric to measure performance needs to be in place. All right, so now that we have the train loop, we've got n epochs, optimizer, model. Now notice here, we also added the loss function. That's a parameter, okay? And then after that, we just have our data. So that's gonna be train TU, val TU, train TC, val TC, okay? So we are ready now to define our function. Okay, so let's take a look. So you guys understand that I explained this. You repeat the process basically, n epochs, and that's just you keep feeding the same data over and over and over, right? And that, as I said to you guys, that took me a very surprisingly, I don't know why, it's simple in my head now, but it took me a very long time to understand that concept, that repeating the data, feeding the data into the model multiple times actually helps. So repetition. So that's where, a lot of people say that neural nets can't be the way our brains work, right? Because you trip on a wire once and fall really hard. Do you do it again? No, right? A neural net would need to trip on that wire thousands of times before it actually learns not to do that. You see the difference there? So there's there's something in our brains that's a little bit different, right? Because we only do it once. All right, so anyway, let's do 4 epoch in range 1 and epochs, okay? Then we look at, remember what we were doing here, we're basically training the model, evaluating the model with the validation data and training the model with the training data. You remember that? So the first part here is train TP, right? We call model, and we provide train TU. Now notice here, the parameters are now the built-in, because when we define the architecture, it creates the parameters for us. You can see that seamlessly done, right? And that's also how Keras does it. You know, it's just people came up with this idea of doing it this way to simplify things. However, you saw before, you can specify the parameters yourself, okay? But I'm about to remove them now and just do it like the easy way. All right, so train TP, model train TU. Then we have the train loss is loss FN, and that still takes the predicted train TP plus the real train TC to evaluate and give you some kind of a value. Is that clear, guys? All right. Then over here, the next part of this, we have the, you know, this, we can keep it as a separate graph. We can take this out here and just say val TP, right? And that's model val TU, val loss is loss FN, val TP, val TC, right? And we have the assert here. Okay, then we have the optimizer zero-grad. We have the train loss backward. Remember, we talked about this before. Remember that up until here, we feed the data forward, right? And the values are predicted in, you know, in the train TP, and then we evaluate the loss, right? But we still need to work our way back. We need to zero out the values with zero-grad, and then we need to do the backward direction, tell it, and then we tell the optimizer basically to step. Right, and then finally, we're going to print out the results every iteration. We're no longer using a return, so take that out. And this is going to be if epoch less than or equal to, let's say 1 in this case, could be 3. And then for epoch percentage 500 equals 0 is fine. So then print epoch. Then we print the train loss, which is going to be train loss.item with that format specifier. And then we have validation loss, val loss.item, and so on. Does this make sense, guys? That's our function. Now we could, if we wanted to, if we're not so concerned about this, we can take it out actually, right? And just use it without it. It should be okay for this problem. So let me go ahead and actually remove this. Remove the assert. Just to make the code a little bit more readable. This also, remember, it's 2 separate graphs, but I can take this out as well. And this just makes it a little bit more easy to read what we're doing here. So we're doing basically the training with the train set, validation with the validation set. We're zeroing out the grad, telling it to go backwards, right? First we go forward, get the results, then go backwards, and then tell the optimizer, do the heavy lifting. Figure out the weights, everything. And that, remember, that involves getting the functions, getting the derivatives of them, and knowing how to do the update. But we don't have to worry about any of that. That's just built in the optimizer itself. So at this point, we have train loop done. Right, so we have train loop done. Hopefully there are no errors. We have the architecture done for linear and for hidden. Then we assigned linear to the model for now, just to try that one out. Obviously, what I'll do after is switch to the other one. We've got the stochastic gradient descent. The parameters are just implied here. From the model itself, the learning rate is defined. We define the training loop parameters. So there's 8 of them. Okay. And then later on, we're going to print out some results just to see what we have available. So I think everything is correct here. So let's try it out. It'll give us an error if there's something. All right, so let's run it. Okay, it ran. All right, so good. So you can see here, we got it done. This is why I like to put some message at the end. It just tells me that everything ran correctly. You can see here, we have the loss function at epoch 1, right? And it is 256 and 430. So for the training data, it's learning from the training data is 256. For the validation data is 431. It's higher, right? Because it's the number of inaccuracies is higher because it only trains on the train data, not on the validation data. Do you see that? But as we continue going forward, you can see that actually the model gets better, right? It immediately at 500, it's already at 29. And then it arrives at about 15. We can probably also give it more iterations to see if it improves even further, all right? But you can see what we want is for this to decrease both for the training loss and both for the validation loss. Okay. All right. So let's go ahead and actually try to do that. Let's increase. You can see it's very easy to just increase the number of iterations. I'm going to increase it to about 5,000 just to see what happens. And actually, I'm going to do like 5,000. Let's try it. You see, as we gave it more iterations, what happened is here, the training loss got pretty low. But notice that the validation loss is not as good, right? And again, this is because the idea that it looks at certain data for training. So obviously, when you evaluate it just on that data, it's going to be pretty good, right? If you build a program that only knows about cars, all right, it does really well with cars, then it sees pictures of buses or motorcycles, it starts to get a little bit less accurate. You see that? And so that's the issue here. You know, the validation data is held out as a separate data set. Does that make sense, guys? Now, the trick is we did this evaluation with the top architecture, that one, right? Now, you've been told, right, that, oh, neural networks are great. They do everything better, you know. Well, you're about to prove that right now. Is it true or not? Now, keep in mind, this data set is pretty small. You know, it's very simple. But in essence, I don't know honestly what's going to happen. But you would think, so the idea at least would be that the multi-layer perceptron would give you better results. You guys see that? So notice that all the code is still the same. And I'm just going to change one thing. And I'm going to convert this architecture from this top one, which is standard linear regression, to this one, which is a multi-layer perceptron, which basically means a neural network with one input, one hidden layer of 13 neurons, and one output layer. Got it? All right, so let's go ahead and do that. So I'm going to do this one over here. And then I'm going to do, so what do I have to change? The model, right? The model, exactly. Very good. So all I have to do is change the model over here. So notice, comment this one out. Uncomment that one. That's it. You just made your more powerful neural network, right? That's all that it should require. So now let's go ahead and try it out. Oops. Oh. I have a. Hmm? When we call it. Oh, yeah. Okay. All right, so Control X, Y. Notice also what's happening here. Slower, right? You guys see that? And that's probably just Scholar. That's, you know, I'm sure my laptop would be a lot faster. So that's, I think that's just that Purdue cloud thing that they have. A GPU would certainly be much faster. So, but what do you notice so far about this data just by looking at it? These values, they're very quickly, they got pretty low, right? But these are pretty high. They're actually worse than the other ones. Would you agree? They're actually worse. The other ones were like in the 26 range. These are 41. Look at these, right? And now if we go to the other one, the linear one, much faster, but look at the values. 12, but this one is 14. You see that? Whereas if this one is 2 and this is 41. This is the nonlinear, the multi-layer perceptron. This is the linear. So what would you say about that in your own words? How would you describe what just happened? How would you describe that? Which one is better in your opinion and why? This is an important question. This is literally an exam type question. Which one of these two is better and why? In your opinion, just based on this data, obviously. What would you guys say? Yeah, go ahead. Just the linear one is better, you think? Why? Mm-hmm. And why is that a good thing? It's a good one. Good answer, right? Because when new data shows up, what do you want? You want one that does well on new data, right? Remember, that's why we have training and validation. So training, the idea is it's training on this data, but we're validating on this data, right? And so in the previous one, it's actually not, I look at it and I actually don't like it very much, right? Because this is extremely good too. Wow, it's very precise. This one is actually 41. It's very off. This is actually there's a term for this. Anyone know what the term for this is? There's a term out there for this kind of problem. It's called overfitting. Overfitting. That's exactly what just happened. We overfitted the data. And it's like a classic example. The training is like extremely good at that data set. So it overfit for that one. In fact, it overfits so much that when it gets new ones, it gets a lot of errors because it's very overfit. The linear functions don't overfit, right? That's the beauty of them. They don't overfit. And so they're more, they do what is called, they generalize better, right? They may not do as great on the training, but they do better on the testing. So obviously, this is a good example of overfitting, but still neural networks would be useful later on. The problem with our case is we just have very small amount of data. It's got a very, very clear distribution, you know, but later on, still you want to try out neural networks as they would usually be better than the linear functions. Does this make sense, guys? This is the example of overfitting. And as I said, it's kind of like this. You know, we built this, so now every time it's trying to fit that curve in there. Imagine we can take this to the extreme in overfitting when we do something like you know, you can literally see that this is way, you know, that's huge overfit. Do you see that, guys? It's too overfit to that data, but the real data may not be like that. You know, or all the data. Remember that you train with whatever little data you have. And so that's just, it's called the sample, right? It's the sample of the entire population, not the entire population. So this was a good example of that, of what overfitting is. We don't want that, and how to evaluate the model. So basically, what would you say about this? You would choose the linear model. If you're, you know, let's say this predicts the stock market and you're going to make money, which one are you going to predict, right? The linear one, the one that you think does better. So in this case, you would be more comfortable probably with the linear. Got it? Make sense? All right, that's your first multi-layer perceptron. So now you can do this, hopefully, and then going forward, we're going to continue using this template, right? The same template, just adding more. As you might imagine, our inputs are going to change going forward. Instead of just one input, one temperature value, it's going to be multiple values, a vector of data. The output also is going to change, right? Because it's not going to be one value that we're predicting. It's going to be what? Classes. Is it cat or dog? Or is it, you know, in the case of CIFAR 10, there's 70,000 images and there's 10 classes. Bird, bus, boat, I think, you know, something like that. And there are RGB also. So that's the next problem that we're going to try to tackle when that is going to get a lot more realistic, and it's going to be a classification problem. So this one is a linear regression problem. Remember that we were still predicting temperatures and so on. Does this make sense? Now we're not done with this script. I still want to do a little bit more of it, but it's 318. It's a good stopping point here. All right, so let's stop at 318. We'll come back at 328 and just do the second part of this. Just wrap up the code a little bit. And then after that, we will hopefully have time for some slides and so on. Questions if you have them. So let's take a 10-minute break. If you can hold your questions, because I also need the 10-minute break. Yeah, and we can talk in the second half. Just start with your questions during the period. Well, you know, the important thing of today I've done, so I'm happy with that. I'll stop the video now also. You just give me a, let me just